Okay, so welcome back to the MCAT support group. Today we're talking about chemistry and physics. And chemistry and physics, it's a bit of a tricky topic for me. This is actually the topic that I struggled with the most. It's the topic that I had the weakest background in. And actually, it ended up being tied for my best score out of the four sections. And I owe that to the fact that because it was like my hardest subject, I studied for it the most. And I think it's a topic that you can really improve a lot in, but it's very intimidating at first. So I was really thinking about how to talk about it, and I think the best thing that I can do is talk about how I like what clicked for me, what made this topic click for me and make sense to me. So first things first, I want to share some of the resources that I had used. So let's see here. Can you guys still see, like I exited out of the full screen, but can you still see like my whole browser?
Yeah.
Okay, so the first one is this equations review sheet, right? And so this equations review sheet is this thing. And it is a really big, I like it because it's color coded and like organized by the topic, right? That the equations belong to. And it is, I don't think you need to know everything here. Like for example, I believe angular motion is not on the MCAT anymore. I think it used to be, but I like it because of how it's organized. And all of these equations are relevant, and you might be looking at this and thinking like, wait, I need to know all of these equations? Well, yes and no. Like the answer is you need to be familiar with these equations, but memorizing all of them is something that can kind of come with understanding the units. So what do I mean by understanding the units, right? The units are the most important part of physics and chemistry. And it's what actually really makes it make sense eventually. If you just approach it as like, okay, I need to memorize this equation and then this equation and then this equation, it's not really going to work. It's going to be very difficult because everything will be too separate. You're going to have to start thinking of it as like, okay, everything is connected. I just need to be able to see the connections. And so units are super important. I'm going to reiterate this several times and you'll see why. So okay, so the other thing is like the thing that gave me the most trouble when I was studying for this was that like everything feels very separate. Before you get that understanding of how things connect, everything feels very separate. Like I wasn't able to understand like, how do Newton's laws connect to like fluid dynamics or electrostatics or everything felt like it felt like each topic was like a new obstacle to climb, and I didn't really understand where it was all going. It's it and it's difficult to see it when you're in the trenches. So I think it helps to these sheets are really good at like condensing all the information and like putting it in a way that you can like quickly find like what you're looking at, especially if you're doing problems, if you're doing passages and you're like, wait, what is this actually testing me on? I want to go review that, right? Then just like we have that big content outline from the Jack Weston site, this is also good because like it's not as in-depth and sometimes you want to start at the surface before you go all the way down to like the specific thing that you're being taught that you're being asked to think about, right? So this is kind of how I oriented myself when I was studying through. So if I had seen like the passage was talking about thermodynamics, I would come and like look at this thermodynamics section and skim it a little bit and be like, oh, okay, I kind of have a better idea of what they want me to think about right now. So units, right? Uh, Units are really, really important because they're how all of the equations actually work. That's something I really didn't understand for a while. I was thinking that, once I memorize all the equations, then I'll be able to do the problems. But it's actually like if you understand the units, you can make your own equations. And that's really um where the critical thinking part of this thing comes in. Because this section is different. They don't really ask you to do that much critical thinking the way that we've been doing in the other three sections, right? Where you read the whole passage and you kind of get a really good understanding of what they're asking for. Here, the critical thinking is how you manipulate these equations and these units. And it was something that took me, was quite difficult for me to get used to in the beginning. But I'm hoping to kind of give you guys an intro to what that looks like. So let's start with one of the most common units that you probably heard of a bunch of times, the joule. Does anyone know what the joule is a unit for?
For energy.
For energy, yeah. Does it measure anything else?
The work also?
Mm-hmm. Perfect. Anything else? Energy, energy, work. Yes, there's like a niche thing. We can also say that it counts, it's a quantity of energy, right? And we can also say that it counts heat or like different types of energy, right? Like heat energy. So actually, no, that's fine. Yeah, different types of energy that we can just say it like that. So what kind of relationships do we know that involve energy? By relationships here, you can see the headline I have written units equal equations equals relationships. So what kind of equations and relationships do you know that involve the joule?
What do you mean? You mean like, for example, like kinetic energy?
Yes, that's an example, right? Because kinetic energy is in units of joules. So what's the formula for kinetic energy?
1/2 mv squared.
Exactly, right? So that's exactly what I'm talking about. This is
Okay.
a relationship, right? The relationship between mass and velocity that gives us energy, that gives us joules. But that's just one of several different equations that involve joules, right? For example, you mentioned work. What is the formula for work?
Force times distance.
Yep, that's another one. What can we do with work? Work, not what equals work, but what's another formula involving work?
I'm not sure what you mean.
I mean, so for example, we said that work equals force times distance, right? Now work, if we, I'm not sure how to ask the question properly, but I'm
Like you
saying,
mean like substitutions, like so if you substitute like mass times acceleration times the distance, like are you talking about substitution, like where you derive different equations in order to get relationships?
sort of, but I'm talking about adding another variable that gives us a different relationship, a brand new relationship.
Oh, okay.
So with work, what if we did work over time? What would that be?
Watts? Oh, no. Watts?
Yeah,
Power?
exactly. Power, watts, right? So that's another relationship that involves work, right? It's not equaling work, but it involves work. It involves a unit of joule, right?
Gotcha.
Mm-hmm. And just another one that I have here, this is obviously not an exhaustive list, but another one is electrical energy, like we talked about. We could have also included heat energy or stuff like that, right? So electrical energy is electrical charge times voltage, right? So look at already in just one unit, how many different relationships we see pulling from all the different branches of physics or chemistry, right? Like this is, so if we go back to that giant map, right? We've pulled something from force, we've pulled something from electro, where is it? Somewhere here. But this thing is so massive that it's like it feels overwhelming. But like when you focus on the units itself, you can be like, okay, I can see where this is coming from, where this is coming from, where this is coming from. So we have work, power, those things, right?
Yeah,
And
if you look at it theoretically, so energy, especially stored energy, is basically how much, like how big the ability you have to do work.
the
And
capacity,
then
yeah.
yeah, and then when you have some kind of a motion, kinetic energy, that's actually translating it into work. I mean, at least that's how I look at it. So that's how I relate that. But using the units is a different perspective that actually helps a lot.
Yeah,
So
I
thank
mean, they're both kind of the same thing because the units are like the mathematical accounting for the
you.
physical relationships in the universe, right?
Okay, yeah.
So yeah, so we're both kind of talking about the same thing, but from different angles. But the more ways that you have to think of it, the stronger it is. So what? Yeah. So yes, that's a good point. They represent the physical relationships that we're talking about. So so these things right here, the work, the force, the distance, right? These are not in the units, right? These are just the concepts themselves, I guess, right? Oh, also I had put that so work over time can also equal current times voltage. And like the electrical energy can also be this other equation, right? Because these things can all be converted with different units. And this is something that you'll get used to over time because it's just like it's kind of like learning a new language if you've learned a new language because each thing has its own role and you won't understand it fully until you see it in many different contexts. So okay, let's just go with this, right? Now what I did was I turned all of these concepts into the units, right? So work equals force times distance is joules equals newtons times meters, right? And knowing how to convert between these two, in fact, probably more often you would be converting from the units to the concept, right? Because when they give you the numbers and stuff to use, they're going to be in units. So you're going to become very comfortable with hooking the unit to the concept and vice versa, right? So we can see here how many different ways there are for joules to be expressed, right? So here's a question, right? We see joules is equal to newtons times meters, watts is equal to joules over seconds, which is also equal to amps times volts. Joules is also equal to, all these equations, right? Then down here we have joules for electrical energy. Joules is equal to coulombs times volts, is also equal to K, Coulomb's constant, times coulombs over meters. Here's a question. What are the units of the Coulomb's constant? How can we figure that out?
I think it's newtons meter squared divided by coulombs, because if you want to have joules, you kind of have to cancel out like the coulombs times coulombs. So it's basically looking at the all the units on both sides. You can find out the constant units. At least that's how I look at it.
Yeah, exactly. I think you're describing exactly what I was getting at. So here we have the equation, right? For electrical potential energy equaling this Coulomb's law, right? And so if we convert all of these things into their base units, right? So a joule is a newton times a meter is equal to the constant times coulombs over meters, right? If we just shove everything over to the other side, then we're going to get what the constant is equal to. And that's really the power of units. So does that make sense to everybody? Like you can derive what something's units are supposed to be based on the rest of the equation, but you can also derive the equation from the units themselves. So it's very powerful in both ways. Um, so let's let's look at a particular type of question that they ask in this section, right? And this is what I meant by like critical thinking with equations. If the electrical potential energy between two equal charges quadruples, describe the change in the distance between the particles. So how would we go about doing this?
Well, first, the distance as in r is inversely proportional to the, you said the u in triples, right?
Quadruples. It
Oh,
says,
quadruples.
yeah,
Okay, so wouldn't it reduce by 1/4 because it's inversely proportional?
yes. Would it reduce or would it quadruple?
Well, R is at the bottom, so I wouldn't think it would quadruple because there's not a direct relationship. Like
Correct.
it's
Yes.
if
Yeah.
I'm making sense.
No, no, you're making sense because it's inversely proportional, right? So so yeah, exactly. So this is how we can this is how they can ask you about these questions without really even giving you anything to plug in, right? Because now they want you to think about the relationships between these two, between these um, between these variables, how affecting one variable affects the other. And this is very common with anything physics related, like what you call it, kinematics or force and stuff like that. They will often do like, if the velocity of this doubles, what happens to the kinetic energy or whatever. And obviously, because it's an exponent, they want you to realize like, oh, it's going to quadruple rather than just double. But yeah, that's pretty common. Um, so and so this is a full-on equational. I don't even know what the correct word is, but if you didn't have it intuitively, if you wanted to write it out, then this is how you would write it out, right? So first of all, we had the information they gave us is that the new energy, the new electrical potential energy is 4 times what the original energy was, right? So we have our first equation. And so what I like to do is I put everything over because we're the change in the distance between the particles, right? So I isolate the variable that's under question, right? The one that's being changed. So we have this is equal to all of this. And then for the new situation, it's the same thing, but then we substitute in the quadrupled original energy, right? And now we have, once we simplify all this, we have that 4 times the new distance is equal to all of this. And so since this and this are now equivalent, then we can just set the distances equal to each other. And then we see clearly that the original distance has been divided by 4 gives us the new distance. So the distance was quartered. And you can use this, stepwise method for any kind of question like this. So yeah, this if you don't have like an intuitive understanding of it, or especially if it's like a very complicated equation like uh Poiseuille's law or something like that,
Yeah,
then
I was gonna ask you about like something like the flow rate, where it's like the radius to the fourth. Those kind of questions kind of trip me up because can you like do one of those where it's inverse, but also there's a power attached to it to see how to break it down?
sure. Let me see how to do. Okay, so I will find an example at the break time, and then we will do that.
Yeah, no
Um,
problem. Thank you.
yeah, no problem. So yeah, that also tripped me up. So then I had done this kind of stepwise method because they often ask about Poiseuille's law, and it's hard to get it intuitively with the exponent sometimes. So we will definitely try to do one of those. Okay, so yeah, so the distance was quartered. Okay, so the other thing to do in these equations is I mean to the other thing that's really important that was really important for me for this section was dimensional analysis because you don't get a calculator on the MCAT, and it was very difficult for me to get used to that. I don't know if you guys are like also like not as reliant on calculators or not, but for me, I was having a lot of trouble just doing the mental math and everything, and I was struggling with the math itself. So dimensional analysis opened up like a whole new um, path for me, I guess, because for example, like even something simple like this confused me immensely because if I was just doing this with a calculator, I would have just done it straight and I would have been like, okay, 2/3 is 0.66 and 6/10 is 0.6, right? And then I have this. But this is like annoying to do in your head. Like it's like okay, maybe I would approximate this to zero point 0.5 and then it's like 0.33, but then it's like it's kind of messy. And especially like this is just two fractions, right? But if you're doing like a whole series of conversions, you're dealing with like maybe 5 or 6 fractions, right? The thing is that if you do dimensional analysis, you can just rearrange the fractions and do the operations in the order that best benefits you, in the order that is the simplest and the easiest. So instead of doing 2 over 3 times 6 over 10, I can just switch these around and I can do 6 over 3 times 2 over 10. Obviously, this is a very simple example, but the point is you would do lots and lots of little switches like these when you're doing a really long like molarity conversion or something like that. And you would also do it with like, when because you're going to be dealing with a lot with the scientific notation, right? So for example, if you had like, if this was 6 times 10 to the first over 3 times 10 to the second, but then you had 10 to the first in the denominator on the other fraction, then you could just mash those 10 to the first together and eliminate them, right? So getting into the habit of doing those small like micro efficiencies, I guess, is really, really helpful for not running into like really annoying math problems that will like arithmetic issues, right? Because you don't have a calculator on the test and you don't have time to like write out long division or any all that nonsense. You just want to make the math as easy as possible. So everybody, like, this is very simple, but it takes a lot of time to get into the habit of constantly rearranging stuff to be in your best interest. And the cool thing is that the test makers themselves set up the numbers so that you can do this. The test makers themselves set up the numbers such that you don't really need a calculator. You just need a little bit of approximation or a little bit of rearrangement. But you have to be able to tell, like, oh, these numbers are going to be good if I do this. That's what they want you to be able to do. So this is a simple example, but the lesson is important, if that makes sense. So obviously here you would see that 6 divided by 3 is 0.5, 2 over 10 is 0.2. So then you say, oh, 2 times 0.2, 0.4, easy peasy. And I'm sure you can see the big difference between this and this. This is something that you could get stuck on for like a minute if you were in the midst of like a bunch of other calculations. So this is a really, really useful optimization. Okay, so let's do some math now that we just talked about math, right? A particle with a velocity of 1 times 10 to the 6 meters per second is placed within a mass spectrometer. Upon entering into the machine, it experiences an acceleration of 4 times 10 to the 12 meters per second squared. The mass of the particle is 4 times 10 to the negative 27 kilograms, and it carries a charge of 2 times 10 to the 19 coulombs. What is the magnitude of the magnetic field? What do we need to know to solve this question? Take some time to read it and think about it. Okay, so I'm not asking for the answer to this question, My question is simply, what do we need to know in order to solve this question?
Well, I have a question before I answer that.
Okay.
If just to clarify, because this is what trips me up. Just the different words. So when they say what's the magnitude of the magnetic field, is that the same as the electric field?
Electric fields and magnetic fields are different, but
Okay,
yeah, they are different concepts, but and we'll get
okay.
into that.
So
Yeah. Go ahead.
okay, so that was my, so it wouldn't be force per charge, like how the electric field equation would be. Because then you would, why would we need velocity? So that's what tripped me up. So I guess I'm guessing because it's different, then that's my answer. Got it.
Yes. Okay. So so yes. So you're going for a good approach, right? You're thinking about, you know, what are the units that we can use, but then you're seeing, oh, we have some units that don't make sense. So what's going on here, right? So what are you really looking for right now? What do you need to know in order to solve this question that you don't know right now? If this was a test and I could give you, if you this was a test and you could phone a friend, what would you ask me for? If you can't ask me the answer to this question, but you can ask me and I'll tell you anything. What would you want to know the most to solve this question?
T.
Exactly. T, right? Because what does T tell you? T tells you the whole relationship, what the magnetic field actually is, right? So if we know the units of t, just like we did before with the um with the k, right? How we in this case we arrived at the k by pushing all the other units, right? But in this situation, we can go from the opposite way. By knowing t, we can arrive at the rest, if that makes sense. I'm not sure if that makes sense, but basically what
It
I'm
does.
saying, sorry?
It does make sense.
Oh, okay. So if we knew the units for t, then we can manipulate everything else and form it such that it would match t. And that's why I'm saying that it's incredibly important to know your units. It's more important to know your units than to know the equations because the units are the equations. The units are just, the predefined bundles of equations that are useful. But if you know the units themselves, it's like the units are the alphabet to the letters and the sentences that are the equations. So if you from here you can see that a Tesla, the SI base equivalent units are kilograms over second squared times amp. Now that if you know this, we can reverse engineer the equation for magnetic fields without even knowing the equation because they gave us all the components. And this is a really, really good way to actually study for these questions because you are expected to know like an entire ocean's worth of of equations and stuff, right? So when you get down to it, when you sit down for an actual question, the question is only testing you on like one of those maybe like 50 different equations that you know. And you're like, how are you supposed to like focus down on what they're actually talking about? And the units are there. The units are the only thing there that will really guide you to it. So rather than going top down from equation, trying to like force an equation onto it, let the equation come to you from the units. That was the big switch for me that made a huge difference in how I approached this section. And I stopped like looking at equations as something to memorize and more as like something to reconstruct given what I'm being given on the test. And one of the ways that I found really helpful to study for was just randomly grabbing a couple of units and seeing, okay, what kind of equations can I make from these units? And that got me into the mindset of like doing it when I saw it on the exam as well. Because like, oh, I've got velocity here, I've got newtons here, I've got this here, that here. I can go this direction, or I can go this direction, or I could do this, or I could do that. And that's really helpful. That's really what you have to do most often with these. So let's go back to uh where is it? Okay, so here we now have our unit for a Tesla, right? And so we know that kilograms has to be in the numerator. So what number are we going to put up in the numerator? Oh, sorry,
The mass.
the mass, right? So let me see if I can write it out. Yes, so let's put 4 times 10 to the negative 27 is up in the numerator now. Then what else can we easily place? We've put kilograms, right? So we've got our kilograms. And then what else do we have to use? Well, we've got meters per second. We've got meters per second.
Okay, so
Mhm.
I have a question.
Yeah,
That A, is that it? This might sound silly, but
let's go ahead.
is that area or is that amp? Because
Good. Okay, good question. Right. And so, okay. That's a great question. That's actually a very, very good question. These units that we're looking at, kilograms, seconds, these are very, very special units. They are special units because they are sorry, let me switch back to the thing. They are the SI base units. And SI base units are the ones that you see on the right here. And what's special about SI base units, you can think of them as like the they're like the fundamental units. You cannot break a second down into any other type of smaller unit, if that makes sense. What I mean, you can have picoseconds or nanoseconds, that's fine. But a second itself cannot get turned into like another unit, if that makes sense. Like seconds, a bunch of seconds can become a minute, but there's nothing below the second.
there's nothing else to make a second. Gotcha.
Exactly. There's nothing else to make a second. And there's nothing else to make a gram. Like, kilograms is just a standard that we use because for some reason, I actually don't know why we use kilograms instead of grams, but there's nothing else to build up a gram. There's nothing else to build up a meter. There's nothing else to build up an amp. There is something to build up area because area is a composite, right? Area is meters squared. So meters squared is the SI base unit. If you can break a unit down into lower order units, it's not a base unit. It's one of these, yeah. So it's one of these composite units. So that's why knowing the SI base units is really, really useful because every composite unit is a composite of the base units. So yeah. So okay, so you pointed out amps, right? So we need to know about so when we come back to our question, so we know we're dealing with kilograms over amperes seconds squared, right? So where do we see seconds squared so far?
In the acceleration, that's it.
In the acceleration, right? So where does the acceleration go? In the numerator or the denominator?
Well,
If we put it in the numerator, if we put it in the denominator, then we would have, let me see if can I write it? Yeah, just imagine there's like a division bar above this. Actually, I could probably draw a line. Let's draw a little line right here. Okay, so let's say that we put 4 times, actually maybe I'll use a different color, then it'll be easier to track. 4 times 10 to the 12th meters per second squared. Okay. If we divide by meters per second squared, where is second squared going to end up going? Is it going to stay here?
The numerator?
It's going to go to the numerator, exactly. Because it would be 1 over meters per second squared. It would end up being.
So seeing that we need time, can we just find time based on the acceleration and velocity? seeing that, because isn't acceleration velocity per time? So that way, because we need time, right? In the like the seconds. And
Yes.
then the ampere would be like, I think coulombs times seconds or something like that.
Hmm.
So that way we could just plug those in and just cancel out. I mean, get the Tesla instead of like doing that. Because sometimes that, I don't know if anyone else have that problem where stuff is in the denominator and the numerator where it's hard to like actually see and it's not straight. So which one do you think is easier in like this case?
Well, what do you mean that it's not straight and it's
Like
harder?
how we had to figure out um if we should put, because it's meters over second square, right?
Hmm.
But
Hmm.
in the Tesla, it's just second squared in the denominator, whereas in the acceleration, it if we put it in the numerator, it'll be flipped because that's already a fraction, like the meters per second squared. So it's
If we
like,
put it in the numerator, it would be flipped.
wouldn't it be flipped? Because you already have meters per second square and you're dividing by ampere times second square.
Where is the second squared in the ampere times second squared coming from?
Well, I'm just looking at what 1 Tesla is.
Right. So, okay. So let me see if I can explain this a different way.
Go ahead,
What?
go ahead.
Yeah, let me see. So let's think about this. This is clearly this part, right? So far, that makes sense.
Yes.
And then this is like our denominator line right here, right? And now, okay, you know what? Let me write these out so it will actually match like what you should do.
Okay.
So then you have 2 times 10 to the negative 19 coulombs. Wait, why is it the same color? I didn't want that. I wanted this one. Okay, and the other value is 1 times 10 to the 6 meters per second. Okay, so here are all the numbers that we have, right? And we have to use these numbers to end up getting the units that we have, right? So what did you say amps was? How are we going to get rid of this coulomb here? What's a coulomb going to do for us? And this is where units comes in super handy. Because if we know what a coulomb actually is, it makes this very trivial. Like, yes, we know that a coulomb is involved in electrostatic equations, but what is a coulomb really, right? And if we go back to look at what a coulomb really is, we'll see that a coulomb really is it's probably up there. Yeah, a coulomb is really a second times an amp. A coulomb is a second times an amp. So if a coulomb is a second times an amp, how can we substitute it into this equation that we're trying to build?
Coulombs times second at the bottom.
Coulombs times a second at the bottom, right? So, whoops. Coulombs times second at the bottom. So let me drag this down. So here we have this, and then we need to multiply it by a second, right? Where can we get a second? Where can we get a second? And this is where like the manipulation of equations is something that you really have to practice. Where can we get a second in this equation? What do we have? What do we technically what unit do we have in the remaining two variables? Yeah,
So you
mhm.
so you have an extra second in the acceleration, and then that would leave you with meters per second, which could cancel out again with the velocity. That what you're getting at?
We haven't, if we did that, right? If we canceled it, where would the second end up?
See, I mean, I can see how we can cancel it out. That's my problem. Where does it go?
Gotcha. So the way that I would think of it is I would break them up if that's um I think it would, oh no, I don't want this one. I think it, no, wait, how do I edit this then? Oh, that's really annoying. I can't edit it after I've written it. Maybe I'm just missing how to do it. But basically what I wanted to do was I wanted to write this out as this is a meter times 1/2. And that, I'm not sure if it may help to recognize like where to put these items, because we have a coulomb, right? And we know that we learned that our ampere is equal to coulomb times second. So if our ampere is equal to coulomb times second, then in the bottom we want to end up with a second. We need to end up with a second. But both of these have seconds in the denominators. So we need to invert this somehow, right? If the second is in the denominator, then we need to put it in the numerator. Does that make sense?
Yeah, I'm tracking.
Okay, so for now, let's just go with the fact that we'll put this like this, right? And if we had written it this way, then we could have easily rewritten it as 1 times 10. Let me just rewrite it out. So we could have rewritten this as 1 times 10 to the 6th meter 1/2. And so in that case, it might be easier to see that this is like a fraction. You're multiplying by 1/2. So then it would just be a second being added to the denominator. So that ends up giving us the unit that we want, because we wanted there to be coulombs times second in the denominator. And here, since we have 1/2, right, we can just move it to the denominator, and we can just put in a second here and get rid of the 1/2 in the numerator. Sorry, I'm taking too long to do this. Do you guys see how this is meter over second right here?
Yes.
Yes.
Okay, great. So this is how you can manipulate the variables to your advantage, because right now we still have no idea what the equation for the magnetic field is. We're just, oh, hi Andrew. Hey. So we have no idea what the equation for the magnetic field is. We are just going backwards and making it ourselves using the units, because we just know what the unit is. So we're almost done here, right? We have the kilogram up top. We have the coulomb times second, which is equal to our ampere at the bottom, right? Now what do? Now we have one last thing to use, right? We've got this acceleration here. And we do see that, you know, second squared should be at the bottom. But we have this meter here. How do we get rid of this meter?
It gotta be in the bottom to cancel out with that meter up top, right?
It's got to be, right? It's got to be here in order to cancel out the meters. But then what happens to the second squared? Is this second squared? We are going to cancel our meters, happily. But what is this actually? This is not just second squared, right?
Does it flip like to the top?
What's up? I can't hear you.
Does it flip around? Like instead of being in the denominator, is it actually in the numerator?
Yes, but the question is why, right? And we want to understand this because this is 1/2 squared, right? If we write this out, if we I don't know, uncompress or expand the unit itself, it's not meter per second squared, but it's meter times 1/2 squared, right? And if we've got this 1/2 squared in the bottom, it can flip up top to just become second squared, right? Okay, wait, hold on. How do I do this? Mm, Sorry, my computer's lagging a bit. Uh, Give me 1 second. Shoot. Zoom is very pain sometimes. Um, I'm not sure why this is happening. Give me okay, guys. Let's let's go on a break for like 2 seconds while I figure out why this is happening. I'm not sure. Let's come back at 6. Let me see what the heck this is. Okie dokes. So we have been talking about units and why units are super important to physics, to understanding physics questions and stuff. And we were talking about how if you know units, that can help guide you for a lot of these questions. So here was an example of a question, right? Where they gave you some various variables and they wanted you to find the magnitude of the magnetic field. And the problem here is we don't know what the equation for magnetic field is. And all we have to go on are these random variables and these equation choices. So paying attention to the equation choices is also super, super important because it's going to guide you to where you need to go, right? And we had said that the most important thing here to know is not even the equation, but what the Tesla itself actually is. This T unit. This T unit is Tesla. And we wanted to know what the units of the Tesla are. So if you know the units of the Tesla, like you do here, it will allow you to manipulate the rest of the numbers to get the value that you need. And that's why we said that, oh, we had shown this huge physics, all these different physics formulas that you can know for this exam, right? But more importantly than knowing all these different formulas is to know how these units are actually what they actually constitute, right? So these are the base units. It's like seconds, amperes, kilograms, meters that you cannot break down into smaller units. You can break down seconds into like picoseconds or whatever, but you can't, like, minutes can turn into seconds and hours can turn into minutes, but seconds can't turn into anything smaller because these are the base units. And so the base units in various different combinations make up these more complex units. So the point that I'm trying to make is if you know how these more complex units break down into base units or like common other unit conversions, that helps you a lot because you can then do what we were doing, reverse engineering the equation basically. Like if we don't know the equation, but we know the units, we can figure out what the equation is supposed to be. So let me actually solve this right now. Okay, so we had said, in this formula, we're supposed to have kilograms in the numerator, right? So what can we put in the numerator? Let me try this again. Hopefully it works this time. Here is, whoops, that's really messy. Okay, so in the numerator, I know that I need to have the kilogram unit, right? So 4 times 10 to the negative 27 kilograms. Okay, one down. Now I need to have amperes in the bottom, but I don't have anything here that's in units of amperes, right? That's tricky. What do we do now, right? That's where you need to know, see that there's a coulomb here, right? And a coulomb is a composite unit, a complex unit. That means that it's made up of other smaller units, right? And if you go back and if you know what a coulomb is a, where is it up here? Yeah, a coulomb is a amp times a second. So if you know what these complex units are actually hiding, then you can easily convert between them by turning everything into base units. So we know now that in the bottom, we need to have an ampere, right? And we can make that with coulomb times second. So in the bottom, we have our coulomb text, dark color. We have 2 times 10 to the negative 19 coulomb, right? Now here's the thing. This is an ampere, right? Is this ampere and this purple unit or variable, are they equivalent? Coulombs and amperes are not equivalent, right? What do I need to do to this coulomb to turn it into this ampere? What did we say was the relationship between the ampere and the coulombs? If we go back up, we'll see that the coulombs times the coulombs, amperes times seconds gives us coulombs. Amperes times seconds gives us coulombs. So if amperes times seconds gives us coulombs, so let's write this out because this can actually be confusing. If amperes times, whoop, why did it do, it's doing it again. Oh my God. Okay, if amperes times seconds equals coulombs, right? What can we substitute for this ampere in the Tesla? What can actually substitute in for this ampere? What does ampere actually equal to in terms of coulombs?
Isn't coulombs times second, isn't it?
Is it coulomb times
Oh,
seconds?
divided by seconds.
Coulomb divided by seconds, right? Ampere equals coulomb divided by second. Okay, so we only have a coulomb. So we're actually not done substituting in for this ampere yet. We need to insert some kind of 1/2, right? So where can we get that? Well, we already have 1/2 here in meters over seconds. So we can put that in as one times 10 to the 6th meter per second. Actually, wait, does it go on top or on bottom? No, this goes on top. Yes, this goes on top. If this goes on top, or does this go on bottom? Hold on, wait, I'm confusing myself. Wait. Amperes equals coulombs over seconds. So we need to divide this coulomb by second. So it needs to go here in the bottom. Yes. No. If it goes on the bottom, it will flip up. Oh man, yeah, that's confusing. It actually needs to go here, right? Or does it need to go there? If it's here, okay, let me think this out, right? If this is up here, then we'll have 1 over second in the numerator. And if we have 1 over second in the numerator, it'll be a second in the denominator. But we don't want a second in the denominator, right? We want 1 over second in the denominator. Okay, does that make sense? Did everybody track like what I just did there? So I was thinking like I couldn't tell where I should put it. I was confused. Do I put it in the numerator or do I put it in the denominator? If I put 1 over so I'm working with this is meter over second, right? Or in other words, this is meter time 1 over second, right? So I'm confused. Where should I put this 1 over second? I know that I want the 1 over second in the denominator, right? So if I put the 1 over second in the denominator, that's equivalent to a second in the numerator, right? And if I put the 1 over second in the numerator, that's equivalent to a second in the denominator. So I don't want a second in the denominator. I want the 1 over second in the denominator. So I'm going to take this thing and put it here. Meters over 1 over seconds. Is that right? I hate math. Meters over,
Right.
that's right, right?
Then you would put 4 times 10 to the 12 power on top.
Yes, and then that would cancel out. Yes, and then everything would
Yeah.
cancel out. Yeah, so you can see why this was the section that I struggled the most with, because I was constantly like getting confused with units and stuff, and that's why I had to practice this one a lot. But yes, you see where I'm going. So 4 times 10 to the 12, and then I have meters divided by second squared, right? So now everything works because I've got my kilograms up top. I've got my coulombs divided by seconds, which gives me my amps that I want. I've got coulombs divided by seconds. And then I've got meters, but the problem, obviously, we don't have any meters in this Tesla, but it's worked out, like she said, because we have meters in the denominator and we have meters in the numerator. So there are no more meters anymore. They both cancel. And then we've got 1 over second squared, but the 1 over second squared is exactly what we want because we want 1 over second squared. So effectively, we have reverse engineered the equation for the magnetic field, for the magnitude of the magnetic field, without knowing what the equation is, just by knowing a single fact that the Tesla is equal to this. And it's a little tricky at first. I'm pretty rusty, so I stumbled over this part. But once you get into the habit of this, it is really, 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 really useful because you can just interconvert between units like it's second nature. And this is a section that really, really requires a lot of practice because the more practice you do, the more you'll get used to doing manipulations like this and knowing where units have to go. So okay, now that we're here, we can do the actual math, and the math itself is not that hard because we can just split it however we want, right? So it's like, 4, we could do 4 times 4 is 16 divided by 2, or we can do 4 divided by 2 times 4 in any way that makes sense to us, right? Because that's the point of dimensional analysis or whatever. But yeah, I mean, at this point we would just basically combine all the powers of tens. So we got 10 to the negative 27 times 10 to the 12. That's 10 to the negative 15, right? Yeah, 10 to the negative 15, and then 10 to the negative 15. Oh, and then these also come up from the bottom. So then we're gonna end up with what? Let's write this out. Actually, yeah, this is a bit of math practice. Let's all let's all try to solve this now and see where we end up. Okay, I solved it and I was getting extremely annoyed until I realized I made a typo. And that can happen too. Did anybody see the typo that I made?
Oh, the 19.
Yeah, the 19. Yeah, and that happens. I actually still don't know like what to do about that. Sometimes like you do everything correctly and you just make like a small transcription error. Like this is not even a I mean, that's not like a mathematical error. Like I just forgot a sign or I forgot a decimal point or something. And actually have no idea. Like that's happened to me and I have no idea how to improve at that because it's not really all you can do is like waste your time and then realize like you screwed up and then go back. At least for me, I don't know if you guys have ever like caught yourself in that way or something like that. But I remember that happened to me like quite a few times and it was annoying. But in any case, if this so this is actually negative 19, and overall the answer, did anybody try to solve it? Well, in any case, the answer that you end up getting is this one. So this might seem a little bit complicated, but it is one way for you to understand the units and understand the equations without having to memorize the equations full bore, right? Like if you forget how an equation is supposed to go, at least you'll be able to go back and make it work. But yeah, it can be a little tricky. All I can say to that is like, practice is really I think practicing in this section makes the most difference because honestly, like I suck at math. I really, really suck at math. I think calculus was my worst subject in college and everything. And I was still able to do really well just from like brute practice and memorization. So, if you're halfway decent at math, all you have to do is like put in the time to actually memorize what you're supposed to know and, you know, go off of that. Yeah. So, any questions before we move on to like a practice passage? All right. So let's talk about the yeah, so the weird thing about this one is I feel like for other sections, like for the car section, I taught you guys a method, and I think that method applies very well universally for like all the passages. And when we went over psychology and sociology, it's all very scientific, experimental driven, and follows very similar patterns of things. In this section, it feels like a lot of small different topics with very like, this is the equation that you should know to solve this particular type of problem, or this is the relationship that we're testing you on, and anything else isn't really relevant here, you know? And so for that reason, this section felt the most overwhelming to me. Um, and the best advice that I have for it is don't go in like reading it and thinking like, okay, I'm going to read this and understand it, and then I will be ready for the questions, because it never works out that way. Just dive into the questions like as even blind even, right? And then like think about, okay, what am I being tested on right now? And then go and learn that concept. So yeah, I would say memorizing the equations or memorizing the units is basically the same thing as we talked about earlier, but memorizing those so that you can recognize what kind of concept that you're working with, and then go through, as you go through your practice problems, you'll be able to target things that you know pretty well and things that you don't know, be able to understand what's helpful and what's not helpful. There's often a question for this topic, especially like what is high yield? And so what people mean by that is like, what can I get away with not studying, right? Which is a fair question, right? You don't want to study things that aren't on the exam. The problem is that almost everything is on the exam. And it's like, the thing is like not everything will be on your exam, right? Like the particular exam that you take won't have everything that you study on it, but it could have a little bit of this and a little bit of that and a little bit of that, right? So my the way that I would say to approach this is to just study the topics that are um that you're most uncomfortable with, right? Because then you won't panic if you see them on the exam, right? And if you get something that you didn't study so much, but like you maybe somewhat remember from school or something, then that wouldn't be as bad as something that you ignored because you thought you could get away with ignoring it, if that makes any sense. Um, so yeah, and that for a lot of people, that's like the entirety of physics that you have to like go back and like review carefully and because I didn't learn like optics and stuff in school, so I don't know what like, or maybe I did and I just like repressed it all. But in any case, that's how to approach studying for this topic. But the good news is this topic is very, very learnable. It's very learnable. Like if you have the time and if you have the right mindset, you can learn it all and you can improve in this topic very rapidly, because it's the one where practice really does give you like immediate improvement in your scores and stuff. So in my opinion, to tackle a passage in this section on the real MCAT, I honestly barely read the passages for this section, because the questions will tell you what's actually important in the passage. They often like structure the passages with like, a little bit of background info, and then they kind of like approach like the idea of the thing. If they have an experiment, they'll talk about the experiment. Obviously, the experiment will be helpful, but like in any case, like that kind of background info is probably stuff that you already know. And like wasting your time reading it is like not the best when you could just read the questions first. This is the only time that I advocate reading the questions first. But it's useful to read the questions first here because you can prioritize what to actually read from the passage, and it will also quickly tell you like, oh, since they're asking about this equation, this is clearly about kinetics, or this is about magnetism or electrostatics or circuits or whatever. It will easily guide you to like the part of your brain that you need to activate for that part. And the other thing is like reading the passage is also not that useful because you need to constantly revisit the passage for the units themselves, right? And it's much more useful to see the question saying, hey, I want an answer of I don't know, newtons, right? If they like, let's say you read the question and they're asking for an answer in newtons, then when I read this passage, I need to find a number in kilograms. I need to find meters. I need to find a velocity or whatever, right? And I think that's a lot. I think it's for me, it helped me a lot with my timing issues in the section, to go question first. Does anybody try going question first for this section? Did anybody experience anything like that?
It varies for me, but there's times I go straight to the questions and it's helpful.
It definitely feels helpful for some sections. I will say, like, if it's like super experimental, there is like some chemistry physics passages that are different where they actually throw an experiment at you, and they're usually organic sections. From what I've noticed, they're usually organic because the organic sections have a lot of like heavy lab related stuff in the chemistries, right? So you've got like I don't know, like purifications, like non-polar polar, that's a thing that I like to do, and purification, solubility stuff like that. So if it's an experiment, then this approach doesn't really make sense. You should like read the experiment and thoroughly understand the experiment the same way that you would for biology, biochemistry, or for the psychology, sociology. But yes, so that's what I'm saying. I definitely recommend like taking a glimpse of those questions and seeing if you can get away with not reading it, and then moving forward like that. Okay, so we are gonna move on to let's see. I don't feel like I gained anything reading the question, but I was doing it like I was doing it for the other sections, but divergence section, different way looks better. You don't feel like you gained anything reading the question in this section or in general?
Sorry, I was using swipe text. Like, well, I mean, I meant the passage. Like, I'd read the passage, and I'd feel like that
You
was
meant the
kind of a waste
passage.
of time.
Yeah. Okay. I see. Yeah. So, yeah, especially in this section, it feels the most like a waste of time to read the passage because a lot of it is just a little bit of background info. Okay, so let's go on to a practice passage. Okay, so where did my Zoom go? Ah, here it is. Okay. All right. Can everybody see this?
Yes, sir.
Okay, so we're gonna try this, right? We're gonna try not even reading the passage and seeing if we jump into the questions. How does it go? So if we treat the interstitial fluid and cytoplasm as two separate wires and the channels as resistors in an equivalent circuit diagram, would adding more of these transmembrane resistors increase or decrease the total equivalent resistance at the node? But without looking at the passage, what do you think the passage is about? And what concepts do you think that this passage is asking you about?
It's more physics, basically with resistors.
Mm-hmm. Yes.
Like, yeah.
Yeah, go ahead.
Yeah, it seems deceiving if you take a look at the passage because it looks like they're gonna dive into the neuron, but then the first question is about physics.
Yep. So that's a very, very common thing. A lot of the passages on the chemistry physics section look like they should be about biology. So there's a famous example of a I think it's like a bicep experiment where like people are holding like different weights, and the entire passage reads like a biology passage, and then the questions are all about torque. And so it's like they want you to be able to mesh those two perspectives, I guess. So that's a very common thing. And it would be to your benefit to think about where in the body could you apply physics? Like where, for example, could you apply like fluid mechanisms, right? With blood flow and stuff like that. Making those connections before you see them on the test is helpful. So we talked about physics, right? What part of physics is this asking about? Did you say circuits?
Yeah, I said circuits.
Okay, yeah. So circuits, right? So let's take a look at these answer choices, right? It says total resistance would increase because the resistors are in parallel. What is this specifically testing you about? There's this particular equation or a particular relationship that this question is checking you on.
Talking about Ohm's law?
Yeah, so is it talking about Ohm's law?
Well, not really. It's saying total resistance. So basically you gotta, I would say based on an answer choice, right? Just looking at the answer choice,
Mhm.
you would basically figure out if you're doing a resistor in parallel or series, and then there's two different ways to calculate each, right? So one is an inverse and one
Yes.
is like direct.
Uh-huh.
So basically that's what it's telling me to figure out. My thing is I can recognize what it's telling me. It's just going about doing it. That's the problem.
Okay. Well, I love how you recognized it because you were able to look at the answer. And remember, we haven't even looked at the passage yet, which is so far we're on a great track, right? We're very accurately identifying the concept in question. Now, the hard part is getting to the correct answer choice. Well, we've identified the concept. Let's see if we can get to the correct answer choice, right? First things first, you correctly mentioned like the inverse resistance and the proper or the normal resistance. Does everybody actually I won't even answer that. Let me just explain it, right? So resistance is a property of circuits or something, right? And so for example, if you were doing this on your own, right, and you didn't know what resistors or what they were talking about, you would go and read about circuits a little bit or watch a video or whatever, right? And resistors, so here we see two different things, resistors in series and resistors in parallel, right? So we have to think about, okay, how do we, and we have total resistance. So the question is, okay, total resistance and resistors in parallel, how do they relate? Well, resistors in parallel add inversely. So it's like if you have a bunch of resistors in parallel, then it's 1 over a resistor plus 1 over a resistor plus 1 over a resistor gives you the inverse of the total resistance. And then if they're in series, then they just add normally. So the total resistance is equal to R1 plus R2 plus R3, right? So the question now is, what is the actual what is the real situation that the question is asking about, right? So let's see. If we treat the interstitial fluid and cytoplasm as two separate wires and the channels as resistors in an equivalent circuit diagram. So far, they said interstitial fluid and cytoplasm as two separate wires. If the two wires are separate, do you think we're looking at a parallel situation or an in-series situation?
Would it be parallel?
Yes, it is. So because an in-series situation, if I can draw this, if an in series situation, an in series situation would look like this, and then we would have resistor 1 here. Sorry for the horrible looking resistor, and like resistor 2 here, right? This is in series, and this only requires one wire, right? But they're saying 2 separate wires. So if we have 2 separate wires looking something like this, we have 2 separate wires, then this is in parallel, right? This looks like it's in parallel. So right away, we've been able to eliminate 50% of the answer choices. So this is how you're going to, this is how we approach every question, right? We eliminate 2, the 2 that are blatantly wrong. Then we have to make a decision. Would total resistance increase or decrease with parallel resistors? And so here's a question, and this is where the equation informs the relationship and the relationship informs the equation. Basically, if you add, and so this is something I did quite a couple of times, right? Where I was like, actually, I don't know. Like, I'm not sure like what this equation means. But the equation itself is 1 over total. It's going to be hard to, I'm going to just write it. 1 over total.
Oh no, yeah, I was gonna say you could also type it, but yeah, you already got it.
Yeah, so 1 over total resistance equals 1 over, R1 plus 1 over R2 or something like that, right? Now here's a question, right? And this is purely a question of like mathematical understanding. If we add a resistor, what will this do? How will that impact the total resistance? And this is something like, if it doesn't come to you naturally, then just do an example and just do it. Like plug in some numbers and then try it and see what happens to the number. I did that plenty of times. So I think that is something that's very powerful, that you can just plug and see what happens to the relationship. So I'm going to give you guys a minute so what I'm saying is, right now you have this, right? And so try plugging in some numbers and seeing what happens if you add another resistor in parallel, right? If we say, okay, I'm going to add 1 over R3. So just try some random numbers. Try like R1 is 1, R2 is 2, R3 is equal to 3. And what is the impact on the total resistance? So I'm going to give you guys a minute to try that. Okay, did everybody have a chance to see what happens when you add an additional resistor in parallel? What impact does it have on the total resistance? Or we can work through it together, or I can give you guys more time if you need more time. You would guess, let's try it out and see what it is. So let's say that our first resistance is how do I write this? Let's say that our first R1 is 1. Let's just say that R1 is 1, and let's say that R2 is 2, right? So right now we have 1 plus 0.5. So we have 1.5 in this first situation. So we have 1 over total resistance is equal to 1.5. So then the 1 over total resistance is equal to 1.5. So 1 over 1.5 is equal to the total resistance. So the total resistance is 2 over 3, right? In that scenario. So in the first scenario, the total resistance is equal to 2 over 3. Then if I add a third resistor, let's say I add another resistor that's also 1/2. Let's say I add another 1/2 resistor, right? Then I have 1 plus 0.5 plus 0.5, that's 2. So now I have 1 over total resistance is equal to 2, or 1/2 is equal to total resistance, right? So in the second scenario, my total resistance became 1/2. By adding a third resistor, did my total resistance increase or decrease? If it went from 2/3 to 1/2.
It decreased.
It decreased, right? Because we went from, it was 66%, now it's 50%. So this is something that if you do it out for yourself, you'll be able to see, oh, this is the relationship. Additional parallel resistors decrease total resistance. And then conversely, you would think, oh, additional in series resistors increase the resistance. And now you know the relationship that you've acquired from the equation. And this is really how you learn this section, just by trying the equations themselves and observing the relationships. So this gives you that
This is
total.
an MCAT study group. Me and Andrew are in it.
Hmm?
When the MCAT study group, me and Andrew. He's on outside.
Someone is unmuted. I'm not sure.
Oh shit, that's me. Sorry,
Okay.
that was me. Sorry.
It's okay, no problem. So yeah, so this is how we would solve this equation, or you would know the relationship already from doing this, right? But does that make sense? How first we deleted the option that wasn't the actual situation, and then we explored the equation to get to the actual you know, is it increase or decrease? A lot of these are like, hey, does it increase or does it decrease? And you just have to go through the equation to see. So yeah. Okay. So any questions about this one, or can we move on to the next one? If you have any questions, please ask, because what we just did is like 75% of the questions, honestly.
Yeah, I have a question. So I just wanted to confirm that the only reason that we knew it was parallel is because of the two separate wires.
Yes, that is
Okay, copy.
that's the main clue. And then we could have also like gone to like read in the passage, like, you know, what does it look like or whatever, and then that would have further confirmed the structure of it. But two separate wires is definitely like, that's a telltale sign.
Okay.
Um,
Sounds good.
okay, good. So I will clear all of this, clear all drawings, and we'll move on to the next. Oh, actually, let's check and see. Yeah, okay. So yeah, they did something similar. For instance, if there are n channels, all the channels of solving for. Yeah, I don't. To be honest, this doesn't really make sense to me. I just plug and chug. But if this makes sense to you, more power to you. Okay. Anyways, so what do we have here? Tetraethyl ammonium is a toxin that inactivates potassium channels. If a neuron with the values in table 1 were exposed to enough TEA, blah, blah, which of the following best approximates the value of? So right here, obviously now we need to, skim the passage a little bit because the previous one, we didn't need to. Notice how we didn't need to go to passage at all for this one. There are many questions like this where they're simply testing your internal knowledge. But for this one, they're like, hey, we're giving you some info in table 1, go look at it, right? So, okay, we have to go look at table 1. So just to skim lightly, laws of physics and chemistry to the human body, talking about axons, nodes of Ranvier. Again, if they talk about stuff like this is the chemistry physics section, not the biology not the biology biochemistry section. So you're not going to be asking about like myelination or neuron anatomy or anything like that, right? You have to be in the right frame of mind. You have to be like, okay, what kind of physics or chemistry questions can they ask me about this topic, even though it looks like a bio topic, right? So we go to table 1 and we see some ion concentrations. Okay, this definitely seems like some good chemistry that we can focus on, right? And they're saying if a neuron, so they gave us some background, a toxin that inactivates potassium channels. Okay, this seems important, right? We are inactivating the potassium channels. And if we expose the neuron and we close the potassium channels, what's the value of Vm? So what is the value of Vm? Well, they gave us an equation here. They gave us Vm is equal to 59 millivolts log all of this stuff, right? And then they said we are inactivating the potassium channels. So in that case, we see that this has got some potassium elements and some sodium elements, right? But if we inactivate the potassium channels, then the potassium elements of this equation are no longer relevant, right? Like they just zero out, if that makes sense, because we block that channel entirely. So in that case, we have to only focus on the sodium, right? So how are we going to solve this? Well, we know Vm. So now we're going to basically plug and chug, right? We've done the conceptual part. The conceptual part was understanding that we need to remove the potassium element. Wait, does that make sense to everybody? That I'm getting rid of the potassium from this equation? Why am I getting rid of the potassium from this equation?
Because it inactivates the potassium channel, then potassium won't be able to flow in or out.
Exactly. That's 100% correct. So we are not going to account for the potassium because there is no potassium flow. Instead, we are just going to focus on PNA and then the concentration of Na out. Oh God, this isn't writing well at all. Okay, actually, okay, I'm not going to write it here. We're just going to go here. So, okay, so we're looking at this now, right? There should be I know this equation. This is the Golden Hodge equation or whatever. There should be a denominator here. Looks like this. So we know we got rid of this. And now, so we have a Na out and we have an Na in, right? So what is the concentration of Na outside of the cell? Where do they tell us to look at? Values in table 1, right? So in table 1, Na outside cell 150. So up here is going to be 150. I should just write it. What am I doing? Up here is just 150. And inside the cell is 15, right? What are we doing for PNA? The permeability. It says each permeability, Px, is proportional to the number of ion X channels that open at that node. What should we plug in for PNA? It's a trick question. We don't need to do it because they'll cancel out, right? So remember that they aren't really trying to trick you. Like they are going to make the equations easy arithmetically, I guess, but they make them hard conceptually, if that makes sense. So here we are. We're at 59 MV log 150 over 15. So what's log 150 over 15?
Log 10, because you divide by.
Yeah, because 150 divided by 15 is just going to be, log of 10. And what's log 10?
Isn't it 1?
Yeah, it's 1. The power that you raise 10 to get 10 is just 1. So 59 millivolts times 1. And that's our answer. Our answer is 60, basically. Because they said, which of the following best approximates, right? So we have some leeway to be a little off. So it should be 60 millivolts. So yeah, that's basically it. So the hard part of this problem is the conceptual part, understanding that you need to get rid of the potassium because the potassium channels are closed. And then from there, it's just plug and chug. And that's really the pattern. You have a conceptual understanding to manipulate an equation and then solve the equation. That's like 75% of these questions. Yeah. So if you can do that, then you're in the clear. And now we've got, so this is a pure conceptual question because they aren't asking about any values or calculations here. So they're saying current is said to be flowing into the cytoplasm when ions move across the membrane. What makes this current in the same sense as current flowing in a battery wire resistor circuit? So again, we're melding biology and circuits, right? That's what this passage is really trying to get you to do. So then we're saying the ions carry electrons even though they might have net positive charge, and current is the movement of electrons. Or the ion, so actually let's go through one by one. Is this correct? The ions carry electrons even though they might have net positive charge, and current is the movement of electrons. What is current?
The flow of electrons.
The flow of electrons. That's correct, right? Is it always the flow of electrons? This is tricky. And this is where being a chemist and learning physics is very annoying because physics. Oh,
the flow of charge, it could be also, right?
Yeah, so physics defines current as positive flow because that's how it was discovered, and they just never bothered to fix it. So so they define it as positive flow. So this is too extreme. Current is not just the movement of electrons, at least according to a physics perspective. So again, like it's annoying, but you have to be able to mesh those two and like compare those two perspectives. The ions create a local change in the electric field, which means that current is flowing. That just sounds wrong to me. It's not that current isn't flowing because of local changes in electric fields, right?
No, because current could charge could flow in an electric field, but doesn't mean that it creates.
Yeah, it's not that their existence creates current. Exactly, yeah. The ions carry net charge with them as they move, and current is defined as charge moving in space. This sounds pretty good because current charge, this doesn't specify a positive or negative charge, just charge, right? And ions do carry net charge with them as they move. So far, this sounds good. D, this is an abuse of nomenclature. The ion, so yeah, I think Damolari had once said like never pick the extreme option, and I think that's pretty. Yeah, that might be on point for sometimes. So this does seem to be correct. Current is not specific to a single species of charged carrier, such as the electron. Yeah. So yes. Yeah. So again, this is a purely conceptual one where they were just talking about, do you understand not only do you understand current, but do you understand current from both the biological perspective and the physics perspective? So that is definitely something that's tricky to integrate into your thinking if you're not, because I assume most of us are all pretty more focused on the biology and the chemistry side rather than the physics side. But this section is gonna push you to understand physics well. Okay. This is a good one. Okay. Suppose that an axon transmits constant voltage signals between two nodes of Ranvier, a distance L apart. A 10% increase in which parameter would require the neuron to dissipate the most power? Hold all other variables constant. So we need to know, what variables are we dealing with? Well, we've got length between the nodes, internal axon radius R, cytoplasmic resistivity P or rho, or all of the above, right? So I had said earlier that one of the best ways to practice for this is to grab random units and be like, what equations can I make with this, right? So what length and radius are kind of like generic. They can be anywhere. But resistivity is a very specific variable, right? And has a very specific equation associated with it. Does anyone remember the resistivity equation?
Is it just the resistance equation that says that the resistivity length and A, or are you talking about just the purely resistivity equation that has to deal with temperature and the constant?
Oh,
That's
okay, good. No. You've got it. So what do you think applies here the best?
well, it's giving me, if not all the parts for the resistance one, the one with the resistivity, the length, and is it the area, the cross-sectional area?
The
Because you have,
area, yeah. So since we have a lot of that, why don't we go with that one, right? That's really what they're trying to, like, if we're in the test maker's mind, we can see, okay, they gave me these, they clearly want me to use this equation, right? Because they're so let's go with that, right? So that equation is resistance equals rho length divided by area, right? So we have rho and we have length, but we have radius. How do we put radius into this?
isn't it pi r square for the
Uh-huh.
area?
Yep. So we just rewrite this, right? We write this as, I don't know how to write pi here. Oh, that works. Pi r squared. Okay. So right now, okay, we have something that makes sense to us, right? What is the question asking us again?
That is asking us for power dissipated, no?
It's asking us for power dissipated. What is the but where's power here? How do we get to power?
Power, can we use the other equations and just substitute for R? Because like power is like I squared over R or something like that. I don't know.
Yeah. No, you're on the right track, right? But yes, that's exactly right. But before we go for like full-on substituting, let's just think conceptually, right?
Okay.
Let's just think conceptually. How does resistance relate to power dissipating? If we increase the resistance, right? How would more power be dissipated or would less power be dissipated? Less power of more resistance, less power of more. I'm not sure what you mean.
Is it inverse? That's what you're trying to say?
Yeah, right. So if we if we look at that equation, right? So power is equal to current times, whoops, sorry. Power is equal to IV, and then we have to substitute in V equals IR, right? So then we have to substitute in, so we have these two equations, right? These are two oh my God, I keep doing this. Power is equal to, so we have these two equations, right? So what we're trying to do is link this resistance here to power, right? Because we're being asked which parameter would require the neuron to dissipate the most power. So we have to link these parameters to power, right? And this is our method of doing it, the equations. So we know that P equals IV, but what is P in terms of resistance? So then P is going to be, if we substitute it in, P, if we substitute this V into this equation, then we get I times R, or of course, I squared times R. Okay, so again, this is resistance. So let's put this in terms of resistance, and we get R equals I squared divided by P. Okay, so now we can go back to our initial equation here and convert the resistance into power. So we can say I squared over P. Does everybody understand what I did there? This is pretty important, because we started with the variables that they gave us, like length, radius, and rho, and we were able to connect that to the equation that you should memorize or know, right? But then from that equation, we need to connect it the way that they want us. So they want us to connect power to these things. So we connected. We had to know these specific equations to connect resistance to power. And now we ask, what is going to, so far, is everybody following? Before we dive into actually answering the question, because this is all just a setup for answering. Does everybody follow the setup? If you want me to explain it again, please say so. Everybody following? Okay.
Yes.
Okay. So now we have some choices. The question is, which of these variables, if we increase it by 10%, is going to require the neuron to dissipate the most power? By most power, I mean like have the most impact on the power variable, right? So these are the two so this is the main variable that we're thinking about. Oh, it changed everything. Okay, whatever, that's fine. I wanted to just highlight the P, but anyway, this is the variable that we're thinking about. So what are the options we have? Let's say we change the length. How is the length proportional to the P? Here it's direct, and then indirect, right? So it's indirectly proportional to the P. So if we change the length, if we increase the length, what happens to the power? Does it increase or decrease if it's inversely proportional?
If you increase the length, it'll decrease the power because it's inversely related, right?
Correct. Yes. So that's number one. Number two, what if the cytoplasmic resistivity right here, this is inversely or directly proportional to the power?
Sorry, what are we looking at?
So we're looking at how does the resistivity
Mhm.
relate to the power, right? We're trying to evaluate each of these variables and
It's
how do
still
they,
inverse.
it's still inverse, right? So far, is there anything that we can like, these are basically the same right now, right? What's the last value? The internal axon radius.
Yes.
This radius, is it going, so here's the question. What's different about this radius compared
It's
to this
squared.
and this? It's squared, right?
Squared, yeah.
Yeah. So if we make a small change here, it's going to have more of a change on the power than this and this. So in this case, it's actually not about invert. They're not even asking, is it increasing or decreasing? They're not even asking about that. They're just asking which is going to dissipate the most power. So in that case, we go for the variable that is going to have the most impact. And obviously, if a small change to something squared is better than a small change to something that isn't squared. or bigger of an impact. Does that make sense to everybody so far? So notice how we did the setup here. We pulled out the equation that we need to know, and then we linked all of the given units to the unit that they wanted. And this is very good practice for you to do on your own. Just with your own units that you know, link them together and see how you can link them and practice linking them in these ways. This is kind of like a puzzle. It's like, how can I get from point A to point B? And it's kind of like, those little line puzzles or whatever. But in this case, it's like you're doing it through formulas. How can you get from power to length? How can you get from this to that? You'll see that there's a lot of different ways and a lot of different paths, and you're not always going to find the best one right away. I just knew to use these equations because I've encountered this many times before. And that's something that you're going to have to do to build that internal memory or internal intuition that, oh, I have resistance, I can link it to power through these formulas. That comes with practice. Yeah. See, because even if you just memorize these formulas, you may not, in the heat of the moment, you might not link it to resistance. You might not.
Hey, I have a question. I'm seeing something. Maybe I'm wrong. So, like you see at the bottom where it says power is equal to I squared times R.
Yes.
Wouldn't it be power is R would be power over I squared? Why'd you switch it? Maybe
power.
So when you listed out the equations, right? So you see where you have P equals IV, then we substitute V for IR. So then now we get power is equal to I squared times R. In order to isolate R, wouldn't we divide power?
You're 100% right. Yep.
Okay.
And that's why I'm terrible at math. Yep. Yeah. So this is the second time I've done this today. Oh my God. I don't know how I got through this section.
Because I was trying to follow, like, I understand the concept though. It's right in terms of evaluation, but I thought I did it wrong. Okay, cool.
No, you please, I'm not infallible. In fact, I'm very fallible. So especially in this topic. That's why I hate this topic. But listen, if somebody like me could do well in it, then you have no reason to fear. Okay, you guys could do well in this section. Because the main part is the conceptual understanding. That's what I'm good at. The conceptual understanding and the actual arithmetic, I tend to screw up a little bit. But yeah, okay, all right. Is everybody okay? Thank you for pointing that out. I really appreciate it. Everybody get on this. All right. Okay. I think there's one more. Let's see. Sorry, we're running a little bit over time. Let's just do this and then that'll be that. So if a node of Ranvier were held at its reversal potential by a battery, and there were twice as many sodium channels open as there are potassium channels, which of the following is true immediately after the potential is turned on? So this is like talking about reversal potential and battery and sodium channels and potassium channels. If I saw something like this, then I would think, okay, let me look at the passage and see if there's like anything to help me here, because I don't really know what a reversal potential is, like off the top of my head. So, and I remember that they had talked about like millivolts and stuff, and equation 1 was reversal potential. So I want to go back and I want to explore that a little bit to see if there's anything I'm missing. Maybe there won't be. Sometimes it happens, but it's worth your time to just check, right? So we knew the first passage didn't mention anything about that. It was just talking about, node of Ranvier, large number of ion specific channels. That's fine. And then let's see. Ion channels open and closed based on their environment and other factors. When a channel is open, it behaves as an ohmic resistor, V equals IR. When closed, insulator, still nothing of value. See, they just throw a bunch of background information. The currents through the ion channels are determined by the electric potential and ion concentration between the cytoplasm inside the cell. If only sodium and potassium ions are present, the reversal potential, Vm, would be predicted by the equation. If this potential were applied to the cell, potassium and sodium would cross the membrane at rates that yield no net current. Okay, this seems important because we're talking about reversal potential. And they had said, if only sodium and potassium ions were present, the reversal potential would be rejected by the equation. And if the reversal potential were applied to the cell potassium and sodium, or were applied to the cell, comma, potassium and sodium would cross the membrane at rates that yield no net current. Okay, so that seems like the big piece of advice that they've given us. So now they're saying, what if we're at the reversal potential held by a battery and there were twice as many sodium channels as there are potassium channels? Which of the following is true? Immediately after the potential is turned on. So they're saying more current flows through an individual potassium channel than an individual sodium channel on average. Does that make sense? What had they said? They said the potassium and sodium would cross the membrane at rates that yield no net current. So right now, the net flow of current is 0 since we're at reversal potential. Okay, I see. This is okay, so this is very conceptual. So this is combining the idea of ion channel. This seems like it's talking about ion channels, but it's actually kind of not. It's actually talking about circuits and your understanding of current flow through circuits. So think of it this way, right? Let's say that we had a circuit. Let me draw out a circuit. Let's say that we had a circuit that was going like this. Let's say that, yes, okay, this is a good idea. Yeah, so let's say right now, okay, let me draw another one. So let's say this is just a rough circuit. It looks like a circuit, whatever. So let's say the red side is the sodium, and let's say the right side, the blue side, is the potassium. Okay. Now, actually, let me just write it so we don't get confused. Okay, and let's say that I just told you that there was like some amount of current flowing through, some random amount of current, like 10 volts of current going through. Sorry, not 10 volts, 10 amps of current. Why did I do that? I don't know. Okay, so if they were going through evenly like this, if there was an even number of paths, right? What would be the current on the sodium side, and what would be the current on the potassium side? There's two different paths, and there's 10 amps, right? And so if we're talking about circuit, do you guys remember like the Kirchhoff rule of junction? I think it's a junction rule. I think that's what it's called. So we have this 10 amps, right? Is all of the current going to go to one side, or is all of it going to go to the other side? In circuits, the current splits. So if the current splits, does it split unevenly or evenly or what? In this case, there's no resistors or anything, so it splits evenly. So we have 5 on the left side and 5 on the right side. Now, the thing is that if there are twice as many sodium channels as there are potassium channels, then the current going towards the sodium side is going to be split up more than it is on the potassium side. And in that case, it should be that more current is flowing through an individual potassium channel than an individual sodium channel, since there are twice as many sodium channels. And the overall, there's no net current. So there has to be an equal amount of current going through on both sides. But since there's an equal amount of current, the potassium side splits it up less. So each potassium gets is shuttling through more current. Does that make sense? And it wouldn't be that the total current through the potassium channels is greater than the total current in the sodium channels, because they told us already no net current, right? It has to be equal. The potassium channels dissipate more power than the sodium channels. Oh God, I don't even want to go through that, but we would have to do the current. No, that's not even true though, right? Because the current is the same. The current, it has to be the net current has to even out. So it wouldn't be that there would be more power dissipated. So I believe it should be A because of how they have done how they describe the channel situation and the fact that there's no net current. Okay, so notice how this is. Oh my God, yeah. So they often like explain it through math, and to me it just makes more sense conceptually. But whatever path works for you works for you. But notice how this whole thing was like a circuit passage disguised in biology, right? So that's a common thing. Okay, anyways, we're 15 minutes over time. Sorry for going over time. I'll stop.